Today we are going to discuss about the Compton effect, which is another experiment which gives you the confirmation of the photon model. So if you remember, in our previous class we discussed about the photoelectric effect, and the experimental observation of the photoelectric effect we had tried to explain those observations which we cannot explain on the basis of the classical understanding of the physics. So it was the quantum theory of light, based on which that the electromagnetic radiation itself is quantized, and the smallest amount of energy is an integral multiple of the h nu. So a photon, which is the smallest amount of energy, is having an energy of E equal to h nu, and we had considered that the photon as a particle. Then only we can explain the experimental observation of the photoelectric effect. So the Compton effect is another scattering phenomena which gives the flavor that really the photon behaves as a particle. So you can see that if we consider photon as a particle, and if we try to collide this photon with an electron, then we can use the kinematics of the collision, which we usually do in our Newtonian mechanics, and we'll try to see that through our known conservation laws, that conservation of momentum, conservation of energy, whenever we do some scattering or collision phenomena. Then we'll try to see what we ultimately get when we consider photon and its scattering with another particle, which is an electron. So naturally, when we consider the scattering, the loss in the photon energy will be equal to the gain in the electron energy, as you can see in this equation. So let's come directly to the pictorial representation of the photoelectric effect. So you can see that this is the incident photon, and whose energy is E equal to h nu. You know, this E is equal to h nu, and the momentum p of this photon, which is incoming photon, is h nu by c. So why h nu by c? Because you know that E equal to pc, you know already, and p equal to, I can write E by c, and E goes to h nu and c. So momentum, we can write either E by c, or I can write h nu by c. So this incident photon of energy E and the momentum p, when it strike an electron which is at rest. Rest means the momentum, its momentum is 0, and its energy is mc square, which is known as the rest mass energy. E is equal to mc square. So, and this is the target, which is at rest with momentum 0. So when this incident photon strike this target electron, then it imparts some of its energy to electron, and then it's scattered. And then it's scattered, its energy becomes h nu prime. So you can see the difference is the energy is h nu prime, not h nu. Okay, so when the frequency changes, the wavelength also changes. You can see this wavy line is a smaller distance, and this is of greater distance. So the energy is changing because the frequency changes when it strikes this. So it imparts some of its energy to electron, and then the energy gained by the electron, which is lost by this photon, it's in terms of its momentum, p is equal to p prime, and the electron is scattered with momentum p and energy m square c4 plus p square c square. So this is the whole pictorial representation of the Compton effect. So we had to calculate this scattering phenomena, and let's see what we get. So to calculate this, we come to this. You can see, you can come to the vector representation of this scattering phenomena. This line goes to the incident direction of the incident photon. So this photon is having energy h nu prime by c. H nu prime by c, its transverse and longitudinal component is h nu prime by c cos phi, which is making an angle phi with this incident direction, and then h nu prime c by sin phi. Similarly, the electron component is p cos theta in the direction of the incident photon, and this is p sin theta perpendicular to the incident photon, making an angle theta with the incident angle. So this is how we are going to explain or calculate the scattering phenomena. So first, we had already told you that the loss in the photon energy when photon is coming and scattering out, so loss in the photon energy h nu minus h nu prime, which is this h nu and this is h nu prime. So h nu minus h nu prime is loss in energy. Loss in energy that will be gained by this electron, so the kinetic energy of the electron. Now we will try to calculate this expression, that the kinetic energy of the electron, which is the loss in energy of the photon h nu minus h nu prime. So what we can do is that we can square both sides, that is E equal to p square c square. So that is p square c square, where is it, 76. So now you can see this first the momentum conservation. This initial momentum is equal to the final momentum. So this is initial momentum is momentum of the photon h nu by c, and then 0, which is the momentum of the photon. You can see from here that this is the momentum of the photon, and this target is at rest because momentum is 0. So, and then after this the momentum of the photon in the direction is h nu prime by c cos phi, and the momentum of the electron is p cos theta. That is why it is written as initial momentum of photon is c, h nu by c, and of electron is 0, and then on the final momentum h nu prime by c cos phi plus p cos theta. Okay, and then in the perpendicular direction the initial momentum is 0, because the perpendicular direction we don't have any in the perpendicular direction. In the initial case we don't have any perpendicular direction, we just have this direction. So in the perpendicular direction the final momentum h nu prime c sin phi, and then minus p sin theta. So you can see this is h nu c sin phi, and then p sin theta is downwards, so that's why this minus this, and the first case this is this plus this. So momentum conservation is this, and the energy conservation you already know is loss in the photon energy h nu minus h nu prime is equal to the kinetic energy. Okay, and angle you know all about. So from these from this step we can you can find that this is a pc cos theta. So you know this is 0. If says this is pc cos theta is h nu equal to h nu prime cos phi. So pc cos theta is h nu minus h nu prime cos phi, and similarly from here this is pc sin theta. Pc sin theta is h nu prime sin phi. So from momentum conservation we have these two equations, and by squaring and adding these two equations we can get loss of thing, and then these are the simple mathematics like we can do. And on the second page you can see they are just adding and squaring both sides and doing all these calculations. So I'll directly come to the final equation, which is the Compton effect, and that is in terms of the lambda prime minus lambda is h by mc 1 minus cos phi. Okay, 1 minus cos phi. So you can see that the implication now the derivation of all these will come. I'm leaving all this derivation for your home assignment, so please note down that the derivation of this Compton effect based on the pictorial representation of the Compton effect, and deriving this Compton effect relation lambda minus lambda prime is your home assignment. Okay, please note down this. You have to submit it as a project. So now let's discuss the significance, physical significance of this Compton effect expression, lambda prime minus lambda. So naturally lambda is the wavelength of the incoming photon and the lambda prime is the wavelength of the outgoing photon, which is going after the scattering with the electron. And then we have h, this Planck constant. This is mass of the electron, because the photon is a massless particle, and this is phi angle. The photon makes an angle with its incident direction. So this equation was derived by Compton in early 1920s, and the phenomena I described, which was first to observe, known as the Compton effect. So it constitutes very strong evidence in support of the quantum theory of radiation. Okay, let's see what is the meaning of this expression. So what equation 2.21 gives you is the change in wavelength, because the change in wavelength, the wavelength after the scattering and the wavelength before the scattering. So there is a change in wavelength which is expected for a photon that is scattered through the angle phi, which is expected for a photon which is scattered through the angle phi by a particular particle of the rest mass. Particle here, what is the particle? Is the electron. So this is the rest mass of the electron. This change is independent of the wavelength lambda of the incident photon. Okay, now you see why it is this, that this change in wavelength is not depending upon any wavelength factor. There is no wavelength. So it is this change in wavelength is independent of the wavelength. Whatever the wavelength of photon which is striking to the electron, and the change in the wavelength is not actually depending on the wavelength. Is it independent? On which it is depending? Completely, because this is constant, this is constant, this is a mass of the particle on which it is scattering, and the angle through which it scatters. So the quantity, this h by mc, is known as the Compton wavelength, which is known as the lambda c. This is h by mc. We can calculate this scattering Compton wavelength. This is for an electron, because lambda c, because we know that mass of the electron we know, h we know, and c we know. So if I put the value of h and the mass of the electron and the value of c, you can find that lambda c is 2.426 into 10 to the minus 12 meter. You can note it as also a small home assignment, that try to calculate the value of lambda c equal to 2.426 into 10 to the minus 12 meter, or it is also known as 2.426 picometer, because 1 picometer is minus 10 to the minus 12 meter. So you try to put the value of Planck constant, mass of the electron, okay, and the value of c, so that you get lambda c is this much. So now the Compton effect, which is lambda minus lambda prime, is lambda minus lambda prime, because this factor is lambda c. Compton wavelength is 1 minus cos phi. We can write this as this. Okay. The second important thing is that the first thing was that the change in wavelength is completely independent of the wavelength of the incident photon. So it's not going to depend, it's independent of the wavelength. The second thing is that, the Compton wavelength gives the scale of the wavelength change of the incident photon. What is saying that this Compton wavelength, which is giving you the scale. Scale here means that this is the measuring tool with respect to which we can measure that how much the change in the wavelength is there. Because from equation 2.3 we know that the greatest wavelength change possible correspond to phi 180 degree. Okay, because when phi is 180 degree, cos phi is minus 1, so this becomes 2. 1 plus 1, it becomes 2, and then we have lambda prime minus lambda becomes 2 lambda c. Okay, so when the wavelength changes, will be the twice the Compton wavelength, because lambda c is 2.426 pm for an electron, and even less for the other particle owing to their larger rest mass. The maximum wavelength change in the Compton effects is 4.8. So now you can see that the Compton wavelength, the maximum value of the Compton wavelength could be will be 4.8 4.82, because when phi is 180, it becomes twice lambda c, and lambda c for electron is 2.426 picometer. So this will be the largest change in the Compton wavelength. Why? Because it depends upon the lambda c, and lambda c is depending upon the mass in the denominator and the mass of the electron. So if we choose the particle other than electron, naturally it is going to be heavier than electron. So this lambda c is going to be less than this lambda c. So it's not going to be maximum than 4.852. Okay. So unless we choose a particle which is having a mass less than the mass of the electron, then only we can have the Compton change in wavelength is greater than 4.852 picometer. Okay, fine. So the first thing was that the change in wavelength is independent of the wavelength, and this Compton effect is giving you the scale of the wavelength change of the incident photon, and the maximum could be change in wavelength could be this 4.852, that is twice times the Compton wavelength, and that is because of cos phi 180 degree. The change of this magnitude or less are readily observable only in X-ray. Okay, fine, because this Compton effect is only significant change in the wavelength you can observe only when we are choosing the X-ray as a photon of the X-ray, because when we choose the photon of wavelength of visible light, the change in wavelength would be less than 0.01% of the initial wavelength. So it's only a significant change you can observe experimentally is only when we can choose the X-ray. And when the X-ray lose energy when they pass through the matter, this is the Compton effect. Is the main Compton effect is the main process through which the X-ray loses its energy when it's passing through the matter. So let's move to the another thing, that how we experimentally observe. The experimental demonstration of the Compton effect is very straightforward. So we can see that this is the pictorial representation of experimental setup. That is a source of X-ray, and we have a collimator to streamline the beam of X-ray when it strikes the target and it's scattered, and we have our detector which can move so that we can detect the scattered photon at several angles. This is a simple experimental setup to demonstrate the Compton effect. Okay, so and that we can find we can see here, or let me give you a very simple explanation for this, that when we do that, that is, this is our atom and this is nucleus and electron. A photon of certain wavelength comes and strike an electron and scattered back, and electron goes off. So when experimentally we try to observe, this is the primary ray, the beam of the primary. This is the intensity and this is the wavelength, and after scattering the wavelength, the intensity of the wavelength is decreased, and then the scattered wavelength we have sort of this thing, and the scattering angle is 135. So this change in this wavelength will get the delta lambda, that is lambda prime minus lambda naught, that is lambda prime minus lambda. So what we can see here is that we can calculate delta lambda change in wavelength like lambda prime and lambda c. This is the lambda c, h by mc, and 1 minus cos theta. In our case we will cos phi. So notice that the delta lambda depends only on theta or phi, not on the incident wavelength lambda. So consider limiting behavior of the Compton shift. For theta equal to 0, which is this peak, for theta is equal to 0, which is this peak. So what we can say that for theta is equal to 0, which is a grazing incidence, that is collision, this delta lambda is 0, because there is no change, no another peak is there. So photon is coming and just grazes the electron and it goes off. So it's not actually striking Okay, so and in another case we can see for theta is equal to 180 degree, a photon comes and it strikes directly and goes off, a head-on collision. So we know that theta is like 2 lambda c, because then theta is pi minus 1 and this is phi 2 lambda c. So in this case this is my initial peak, and this is another peak which is at 180 degree. For 180, for theta is equal to 180 degree, this is delta lambda, which has to be maximum. The same thing you can find in this notation, that theta is equal to 0 when theta is phi is 90 degree wavelength change, theta 45 degree wavelength change, and theta 135 degree change in wavelength. And obviously one more thing I would like to emphasize, that you can see here, if you see that the results shown in figure 2.24 exhibit the wavelength shift predicted by equation 2.21. Figure 2.24 is this figure. This is change in wavelength figure, and but at each angle the scattered X-ray also include many that have the initial wavelength. That means these wavelength, throughout these wavelength we have many initial wavelength. What does it mean? That when this initial wavelength is coming out, so all the electrons are not tightly bound. Okay, so when we drive this expression, this lambda minus lambda prime, it is supposed that these electrons are loosely bounded, they are free to move. Okay, only when we get the scattering experiment. Otherwise what will happen, that when this photon, we suppose that when this photon strike the tightly bound electron, which is the innermost electron, then it will strike it, and the whole atom will bounce back. The whole atom will bounce back. Okay, like in the photoelectric field, you see the total amount of energy is imparted to this electron. It gets off. This electron gets off of the system. So if we consider the scattering, then if this photon strike the tightly bound electron, then what will happen? That the whole atom will get rebound, and in the expression here, in place of the mass of the electron, we have to consider the mass of the total atom, and in that case we are not going to get the change in wavelength which is observable experimentally. Okay, so this is one point which we must remember, that while we getting these peaks, so within these peaks we are getting a lots of initial wavelengths also.